All right, so the classical prediction is this. The Rayleigh-Jeans equation predicts, okay, that the so-called spectral density, this is really just proportional to the intensity of the radiation. If you are going to plot the intensity of the radiation versus frequency, okay, you'll find that the analysis of this using classical mechanics will show that right here, okay, versus frequency, the intensity, spectral energy density will increase. So the intensity of the radiation increases as the square of the frequency. Okay, that's based on classical mechanics. So what that means is the higher the frequency, the more intense the radiation coming out of a black body. That means the very high frequencies like X-rays will have, or ultraviolet radiation, X-rays will have very high intensity. So that's a prediction. So that's why this is known as the ultraviolet catastrophe. It doesn't actually happen. If it were to happen, that's a major catastrophe because you'll all be glowing with infinite amount of radiation, and very deadly ones at that. You'll offer ultraviolet X-rays. Okay, so that is a classical prediction. So that's the anomaly about the black body radiation. New here is the frequency of the radiation. So what you're plotting here, the spectral density, that is the energy per unit volume per unit frequency. Okay, so if you were to integrate rho versus frequency, okay, from zero frequency to infinity, that area right there, okay, what would that be? So you have energy per unit volume per unit frequency. That gives you the energy per unit volume. Okay, that's called the energy density inside your cavity.
You said the higher the frequency.
The higher the frequency, okay, the more intense the radiation inside the cavity. Okay. Now, in this expression, this term right here, 8 pi nu squared over c cubed, okay, that is interpreted as the number of cavity modes per unit volume. What's a cavity mode? Well, it's a way for electromagnetic radiation to exist within the cavity. Electromagnetic wave inside the cavity is said to be a standing wave. That means at the boundaries of the cavity, the wave will approach zero. So what you have there is a standing wave. You've heard of standing waves in your physics classes, right? So the higher the frequency, it turns out from the analysis, is the higher the frequency of your radiation, the more cavity modes, the more ways you can make a standing wave with that frequency within the cavity. So that's why it's directly proportional to nu squared. Okay, now this average energy of the oscillator, okay, expression right here is just kT. It's directly proportional to the Kelvin temperature. K is Boltzmann's constant, and if you recall from freshman chemistry, Boltzmann's constant is just the gas constant divided by Avogadro's number. Okay, so that's just directly proportional to temperature. So you can see for a given temperature, okay, this is the expression for the spectrum. You have a spectrum that will just rise to infinity as frequency increases. Okay, in other words, this is saying we're all releasing an infinite amount of light, basically, light energy. So that's a problem there. What's the actual experimental spectrum? It looks like this one right here. It actually goes through a peak and then goes back down. This is versus wavelength. This is versus frequency. So if you look at this graph right here, this one right here, this is versus wavelength. Okay, so it goes to infinity at short wavelength. If you look at this graph right here, the classical prediction says it goes to infinity at high frequency. And the actual experimental spectrum is given by this curve right here and this curve right here, versus wavelength, and this one right here is versus frequency. Okay?